It will be presented by Professor Weihua Jiang. He is from Nagaoka University of Technology. Nagaoka, from my opinion, is not so large Japanese city, but has an outstanding University of Technologies, and Professor Weihua Jiang is Director of Extreme Energy Density Research Institute at Nagaoka Institute of Technology. The talk name is Pulse Power Generation for Gas Discharge and Plasma Application. Please, Professor Weihua Jiang.
Thank you very much. Can you hear me?
Yes.
Thank you. Good morning, ladies and gentlemen. First, I would like to thank the organizing committee for giving me this opportunity. I appreciate it very much. It is my honor to present this plenary talk at this conference on the first day. The title is Pulse Power Generation for Gas Discharge and Plasma Application. So it's actually not particularly on gas discharge, which is pulse power generation. I hope our attendees will be interested in this presentation, because we believe that actually most of the people working on gas discharge use a lot of pulse power generators. And many of the pulse power generators are actually developed for some kind of gas discharge, at least for our pulse power generators. And I'm sorry I cannot go to Ekaterinburg, although I would like to go very much. But for the reason that we all know, right now we just cannot travel. So I miss the conference very much, especially when I heard about the excursion and the conference dinner. So I do hope that I will see you soon, next time in person. And I hope I will find an opportunity to visit Ekaterinburg someday. And I hope you will find opportunity to visit us in Nagaoka when this COVID thing is over. As Chairman introduced, we are Nagaoka University of Technology. It is in a city called Nagaoka. It is indeed a small city in Japan, but it is not really far from Tokyo, as you can see from this map. And it's called Nagaoka University of Technology, which means it is a university on engineering only. And in this university, we have a research group called Extreme Energy Density Research Institute. It started about 40 years ago, in early 1980s, working on high-power accelerators, nuclear fusions, and high-power microwaves. We still have our large pulse power generators here in the photo. Etigo 2, which is a terawatt machine. It is the only pulse power generator that can generate output higher than 1 terawatt in Japan. And we are right now using more of this relatively small pulse power generator we call Etigo 4 for high power microwave generation. But today I would like to talk about development on compact pulse power, because in recent years we are doing a lot of work in this area for two reasons. One, there are many good customers in Japan who need this kind of compact, repetitive pulse power generators. And second, we have very good access to top-level components in Japan, such as semiconductor devices and good magnetic materials, which are also very important for pulse power generation. So today, I'm going to talk compact pulse power. Speaking of compact pulse power, we all know that there is a very popular scheme called magnetic pulse compression, or MPC. It was developed in 1990s, primarily for laser driven, especially for excimer lasers. Like this photo actually shows a company, right now is selling this, a company in Japan is selling this generator for laser application. And this kind of pulse power circuit is so popular that when people, for certain years, when people talk about compact pulse power generator, they immediately think about MPC. Until about 10 years ago, or a little more than 10 years ago, when people started developing compact marks and then solid-state LTD. First, I have to mention that these are two different approaches for compact pulse power generation. Just as we can see from these simple cartoons, on the left-hand side, we have the pulse power compression, which means by compressing the time width of a certain energy, we can get high power. This is very typical on textbooks. But for both marks and LTD, it's actually based on the so-called power adding, which means the pulse width has been determined from the very beginning. We just put many small pulses together to get a large pulse, large enough that we need. So because of this difference, we can say that most of the MPC generators has integrated structure. And compared with this, marks and LTD both have modular structure. And traditional pulse compression need energy transfer from capacitor to capacitor and to capacitor. But for power adding, it's direct output. There is no intermediate energy storage. And because MPC use magnetic force, which limit the parameters. And compared with this, both marks and LTD can have very flexible output, both in current and voltage. So they are very different generators based on different principles. But of course, MPC, especially in Japan, it is very mature. As I mentioned, it's actually being sold on the market. But although both marks and LTDs are kind of available, but there are still many technical challenges that are being solved while people are continuing developing them. And relatively, if we compare these two methods, MPC is kind of relatively low, good for low impedance output. And both marks and LTD are relatively high impedance sources. And MPC use capacitor as energy storage. Unless we use any kind of pulse-forming circuits, we get sinusoidal waveform. For marks and LTD, if we turn the switch on and off properly, we can get kind of a rectangular waveform. And these are the major differences between these two pulse power approaches. Today, I'm going to talk both marks and LTD because we are working on both of them. If we compare these two methods, marks and LTD, here I've shown some very basic circuits, but these are some typical examples. There are many variations for both marks and LTDs. But basically, we can say that marks is a capacitive adding, and LTD is inductive adding. Both have modular structure, and marks has a big problem because of elevated potential for different modules. But LTD, because of its inductive adding, all modules can be connected to the ground. Then this is a huge advantage for LTD. On the other hand, we don't need magnetic core for marks, but for LTD, we need many, many cores, which are both heavy and expensive, and they limit the pulse length. So I'm going to start with marks generator. Well, of course, we all know it's been around for nearly 100 years. But for most of these 100 years, the Marx circuits are switched by spark gaps. Until very recently, we are using semiconductors. Of course, we cannot compare semiconductor switches with gap switch. And we do not need to compare because they are for different purposes. The whole solid state marks may not generate the voltage as high as a single gap switch can handle. But for both gas discharge and plasma generation, we usually need voltage like 10 kV or a few to several tens of kV. So close enough, but still have a lot of work to do by using semiconductors, because there's no single semiconductor switch can switch 10 kV, well, at least very fast. So we need a certain method, and Marx is a typical one. If we compare solid state with traditional, of course we can say very high repetition rate, and it's possible to switch off, and most importantly, reliable and durable, because we are talking about industrial application. So for solid state marks, this is again the circuit I have shown on the last slide, but it's called standard marks. We just replaced the gap switch by solid state switch. But this is too simple and not so flexible, not so easy to use, although it's very simple. We use only one switch per module, or the number of switch to capacitor 1:1. But actually, in most cases, we use more switches, because there are solid-state semiconductor switches. It's not a big deal to increase their number, as long as we find it's interesting or useful, or find it necessary. So the lower one is a very typical circuit we are now using. We use two switches per module, one for charging and one for discharging. With this, we can do a lot of operation variation. So I'm going to talk more about the circuit of these marks. Starting with the switch. It is important we standardize everything, which means we make everything exactly the same so that we can use them everywhere we need. For example, for switch, we use this board, and this thing is the same everywhere. If we need a switch, we just put this switching board there. For this one, we're using I'm going to introduce the switch for more detail. Anyway, if we go to module, a module is a part of the circuit like this. It uses two switches. As we can see in the picture, we have two switching boards, and it has a capacitor. And with some other components, we have this, we call it module. And we just copy this module to make a Marx generator like this. In this picture, we have only 6 modules, but we can put many, many of them on top of each other to make a relatively large Marx generator. How large we can go, that's a very important question which I'm going to mention later. I'm going to answer later, but first I'd like to give more detail about our switching board. It is combination of 3 MOSFETs connected in parallel. It is controlled by a single optical signal sent through a fiber to this board. Each MOSFET is driven by a driver IC, so they all switch together at the same time in order to get higher switching current. And the power for the drivers are sent to the board through a DC-DC converter, so that this board can work at relatively high electrical potential. It is totally insulated from the ground level. And if you look at the module, as I said, it's part of the circuit, and we just put many of them together to make a marked generator. Each module needs 3 things from outside. One is the high voltage supply. Second, low voltage supply for the power of the boards themselves. And the signal, which comes from the optical. So there is no problem with optic signal. There is no problem with DC charging because we charge from the ground level and it goes through these diodes to every module. There's no problem for electric insulation. The only issue comes from the low voltage supply. It's only 12 volt, but how to deliver to all those modules at high electrical potential. And here we see if we have a marked generator here, the electrical potential goes higher if we go to the higher levels, but we can charge them through many diodes with power supply on the ground level. For the driving power supply, we need another low voltage supply and convert them through either DC-DC converter or transformer. But the issue becomes very difficult if these marks can generate a very high voltage, because here we need good insulation between high voltage and ground level. We solve this problem by using, we call it step-down converter, which means we do not need anything from the ground level, like this. Each DC-DC converter receives high voltage from the marks module, convert it to low voltage, and send it back to the marks module, so that if the marks is charged by high voltage, it can work. Do not need any other power supply. With this, we can build very high voltage capacitive marks generator. And this DC-DC converter has a basic structure like this. This is a block diagram for our DC-DC converter, and this is the real picture. It's relatively compact and inexpensive. We can make many and put one to each marks module. The only issue is we can see relatively low efficiency by converting the high voltage to low voltage. Well, actually, this power is very low. Each marks only need several watts, or maybe a few tens of watts of electric power to work. So even with relatively low efficiency of this conversion, we do not have any real efficient issue, because marks usually work at much higher average power. And we do not have any thermal issue. We do not actually need to cool this DC converter. Anyway, for our marks generator, we first like to introduce our CES marks, which means capacitive image storage marks generator. I have 2 groups of switches. One is called CS, or switch for charging. The other group is called SD, or switch for discharging. Usually the switches for charging are turned on so that we can charge every capacitor like this. And when the charging is finished, we turn off the charging switch and turn on the discharge switch. So just like typical marks, we get all capacitors connected in series. So here it is important, this time sequence is like this. When the charging is happening, the discharge switch must be turned off. When we do discharge, the charging switch must be turned off. If we can do this, our mark generator can generate high output voltage of charging voltage times the number of modules. Well, this is what we expect from our mark generator. And this is an example. It is 12 module marks using capacitive energy storage. We have a little more than 10 kilovolt with a little spike at the beginning. This is for our discharge application. Second case is IES. I'm sorry, I have to move a little faster. For IES, well, we just turn on the switch and let the capacity discharge inside the module to charge the inductors. And when we turn off the switch, we get all the inductors connected in series, and we can get output voltage generated by these inductors. And this is an example. Only 4 modules, we get more than 9 kilovolt of output voltage. Finally, both IES and CES, we use both capacitors and inductors. How to do this? We charge the capacitors by turning on the charging switch. Let the capacitors charge. And we turn on the discharge switch without turning off the charging switch. All switches are on at this time. So we get current inside each module. During this time, the energy is transferred from the capacitors to the inductors. By turning off the discharge switch, we get all the capacitor and the inductors connected in series, and their voltage are actually in the same direction. In this case, we get output voltage higher than charging voltage times the number of modules. Actually, it's much higher than this voltage. So this is what interesting with this kind of Marx generator. And here is an example. With only 4 modules, we get 9 kilovolt peak voltage, because this actually caused by the spike generated by the inductors. So with only limited time left, I would like to go to our LTDs. And I don't need to explain about the principle, because as I know, the first LTD was built in Russia. But I just want to bring our attention to the fact that there are 2 kinds of LTD. One is large LTD, the other is small LTD. And we are working on the small LTD, which is switched by semiconductors. And they are highly repetitive, and they can be switched off, and they are reliable and durable, although they have exactly the same equivalent circuit as large LTD. So if we look at the small LTD, they have exactly the same structure. From the center, we have the core, the capacitor, the switch. We need, of course, the drivers, and some control and charging units. We need 3 things from outside for each module. And they are the same with our solid-state marks, but as I mentioned, for LTD, we don't have to worry about insulation because every module is connected to the ground. We just directly connect everything to the module. Actually, we do not need optical. We can do electrical triggering. But we always do optical mostly for the purpose of noise prevention. Anyway, I skip the basic principle because of the time, and I think people here understand what LTD is. And this is our solid-state LTD, and we have made many of them for the last 10 years. And they are actually published in many of our papers on IE transactions on plasma science. So they look exactly as large LTD, but just smaller, much smaller, and very stable and reliable. And they can be switched off When we switch it on, the voltage come up, and we switch off, the voltage come down before the capacitor is finishing discharge. Actually, during each house, each capacitor only only generate or output a very small percent of its stored charge. As we can see, this slow drop of the voltage is actually caused by the capacitor discharge. If we change the time length of the signal, we can see the change of the output pulse until we see the saturation of the magnetic core. For this case, we cannot generate wider pulse than this one because our cores are saturated. On this, we use a larger core, or we operate at lower voltage. Anyway, we have developed different versions of our solid-state LTD. For this one, we use relatively powerful MOSFETs, which can generate 20 kilovolt and 3.5 kiloampere output with variable pulse length. We are limited by the saturation of the cores, as I mentioned. And our largest LTD stack is this one. It has 75 modules using more than 1,800 MOSFETs at the same time to generate more than 50 kilovolt of output voltage. But more important is we can also separate them into two stacks so that we can get the voltage, higher voltage, because we have two stacks in parallel. Each can generate 3.5 kiloampere. In this case, we get total of 7 kiloampere output current, but of course half of the output voltage. So for LTD, this is the convenient part. With different way of stacking up them together, we can make different kind of pulse generator for different output parameters. And we can do bipolar LTD, just put them different modules in different direction. We can do bipolar. I skip the explanation about the principle. Actually, we have 5 modules on the top and 5 modules backward at the bottom, so that we can get both positive output and negative output whenever we want. And well, also we can share the core for both positive and negative circuit boards. It's a different way of doing bipolar LTD. And in this case, we can generate a very high frequency burst bipolar output because we don't need the restoration of the magnetic switch because the positive and negative pulses will do it by itself. So as the timing is limited, my last point I want to make is pulse shaping, which is intentionally shifting the timing of each module so that we can get a waveform that we want. This we call pulse shaping. For doing this, we have to trigger each module separately. And this is done by using FPGA, a very special circuit. It has many pins. Each pin we can control by using our program, generate a special independent signal to control each module on the LTD. And with our program, we can generate any waveform that we want, or we can change the waveform during operation. And we call this a smart LTD, because we have a feedback, we have automatic real-time feedback through ADC or analog digital converter. And FPGA can figure out another waveform and send it back to LTD and do another discharge, which is like this for our coaxial discharge, which is used in many cases for gas or liquid treatment. The LPG can figure out the best sequential for the next waveform. For example, if we want current to be close to 40 ampere, after several shots, it actually figured out a group of signals. And by sending these signals to the LTD, we get a waveform like this. We can also change the current to a different level, and we can change it. Actually, not just current, we can actually ask the LTD to do a constant impedance discharge for a certain time. Well, anyway, I skip our result on the water application to the water treatment and go directly to the summary. I see the timing is almost up. So in this presentation, I have been talking about marks and LTD, but they are both switched by solid-state devices. Although these circuits are originally developed by, well, for relatively large power systems, by doing compact marks and LTDs, we can do a lot of new things, like I have mentioned today. For example, we can do both CES marks and IES marks and CES plus IES marks. And for LTD, we can do digital control and bipolar LTD. And finally, we can do pulse shaping, which we are now calling it smart LTD. That is what I have for today, and thank you for your attention. Thank you for this opportunity.
Thank you, Professor Jiang, for a very interesting presentation. Also, I'd like to thank you for very good timing of your speech, because sometimes in Russia it's difficult to reach such good timing. So we have enough time for questions. Did you hear me?
Yes.
Yes, okay. Please, questions from auditorium, questions. Yes, please read.
We have one question from our Zoom chat, from Dr. Krasik. Thank you for very nice and clear presentation. And quick question, how reliable these generators in the case of short circuit?
Well, this is a good question. Depending on which one you are talking about. For the IES circuit, there is no problem, as we know, because it's inductive energy storage. There is no problem with a load shortage. But for CES, it's always an issue. If the load impedance too low, we may have overcurrent on the switches. We have to have a special separate protection for CES marks. For LTD, well, it's much easier to do this because our LTD system usually has more switches, which means it has higher current capacity. For most of our discharge application, we do not have this issue. And for both cases, I want to mention one fact, because we do a lot of discharge using this system. And with our industrial partners, we always put the generators at a different location with our load and connect them with coaxial cables. And the cable is long enough that the actually power source do not see the load. They only see the coaxial cables. So whatever happened on the load, we do not have any problem with our busbar generators. Thank you for the question. I hope I have answered it.
Please, another question from auditorium? No questions? I have one question. Please, Professor Jiang, could you tell something about pulse power applications which are more promising from industries, for industries?
Well, first, today I'm here to talk about generators. And second, we do have a lot of industrial partners who are using our generators. So, yes, we have some ideas, but we actually do not know the details. And they do not even let us to know the details. So, as far as I can tell, one is for ozone generation. It is now a very interesting application. So for our MAX generator, our partners are actually using them for ozone generation. And we have different generators. They are testing different generators for the results. And for our LTD generators, it is mostly used for water treatment. It is also a kind of gas discharge because it's not directly discharging the water. It's kind of discharge on the surface of the water or in the shower, in kind of shower in the air with a lot of droplets of liquids. So it's a shower of liquids and kind of gas discharge. So these are the applications that we can see. But there are many details that we do not know, and they do not let us to know. That's what I can say today.
Thanks a lot. Let's thank the speaker again.
Thank you very much.
We also hope that sometimes we will see you, maybe at Ekaterinburg, in face-to-face
Thank you.
format.
Thank you. I look forward to seeing all of you. Bye-bye.
Best wishes to you. Thank you.